Hi guys, welcome back to Data Every Day. Today we're looking at a data set of data from the Melbourne housing market, Melbourne housing clearance data from January 2016, and basically we have a bunch of different properties, and we're going to try to predict the price of a given property. So this will be a regression task, and we'll use all the other data. There are actually two files. One has more columns but fewer rows, and this one has this one seems to be like a cleaner version. I think I'm just going to use this one. It has more rows, but the fewer missing values, and just a cleaner set in general. So we're going to use all the data in this, all 12 columns that are not the price column, to try to predict the price column. So let's get into the notebook, and we're going to use a multi-input TensorFlow neural network to make our predictions. So I'm going to import NumPy and pandas just to work with the data, and then for pre-processing I'm going to use the tokenizer and pad sequences function from Keras, and the standard scaler and train test split function from sklearn. Then we're going to construct our neural network with TensorFlow, and we're going to evaluate the performance afterwards with an R-squared score from sklearn. So let's go ahead and import all that, and then we'll load in the data using pandas.readcsv. We can grab the file path over here. Remember, I'm going to use the prices less CSV, so I'm copying that, pasting it in, and let's take a look. Alright, so we have 63,000 rows and 13 columns, and let's just get some info on the data. Okay, so you see we have a decent number of object columns, right? So we're going to have to do some sort of encoding schemes on these. And then it looks like there are no missing values except for the price column, which has some. So because price is what we're trying to predict, we're going to drop any rows that are missing. Basically, what's the point of like imputing a value for price and then trying to predict it? You know, that's a bit counterintuitive, so we're just going to drop those rows. Let's get on to pre-processing, and I'm going to create a function called preprocess inputs. It's going to take in a data frame, and it's going to return x and y, where y is what we're trying to predict, in other words the price column, so y equals df sub price, price, like that, and I'm going to make a copy of it. And x is going to be everything except the price column, so I'm dropping it from axis 1. And we'll make a copy of that as well. So like this, and then we're going to return x and y. And at the beginning, before I do any pre-processing, I'm going to make a copy of the data frame. So now we can get x and y from pre-process inputs. And here we're going to pass in data, right? Alright, so x looks like this, y should be everything in the price column only, and you can see there we have some missing values. So let us get into, alright, so the reason I made this function, right, is just so that we can add a bunch of pre-processing steps inside the function and just do them all in one go. So down here this is splitting df into x and y, and then I guess the first thing we can do is drop those missing rows, right? So because we know the only rows with missing values are price rows, we can just drop any missing rows from df using the df.dropNA function. This will drop any missing values it will drop any columns or rows depending on what axis we specify. Here is axis 0 for rows, so this will drop any rows from df. And we're going to reset the index afterwards so that the indices don't go missing when we drop them. And we're going to include drop equals true inside that so that we don't use the old indices as a new column. So let's just comment this, drop rows with missing target values. Whoops, alright. Now if we run this, and run this, we should see, if we check the isNA, this will be true for any entry that has a missing value. We'll sum across it to get the total number of missing values in y, and there are no more missing values. So we are free of missing values. And you'll notice also in X, if I do the same thing, you'll see there are 0 missing values in each column as well. So missing values are taken care of. Next, we could start encoding, but first I want to generate some features from the date column. This is the only thing that we can't encode as it is. I mean, we could actually encode it as a single ordinal feature that represents the recency of a given record. So it would go from most distant in the past to most recent. But we lose a lot of information that way, such as time of year. It just gets converted into a single continuous range if we do it that way. So what I'd like to do is split off the year, month, and day into their own separate columns. So let's do that here. We'll say create date features. So what I'm going to do, we could go in and just index the, we could use regular expressions or grab just the numerical data using like indexing. But there's a better way, which is turning the column into a date time column. So here's the date column, right? Just this column. And we're going to use pandas.toDateTime. And we're passing in the same column. And what this will do is convert it into a column that has here, watch it, for example. If I do x subdate, and we use this toDateTime function on it, it will turn into this, which we can then apply lambda functions to, where x is going to be a given entry, and instead of doing x sub 0 through 4 to get the first characters of the year, we can actually just say x.year. And that's a special feature of the datetime column, and it will return the year as an integer. So this is a very useful way to do it. Over here, we can just create these new features. We'll have year. We'll call the column year, and that will just be df sub date dot apply lambda x.year. And we can do the very same thing for month and for day. So this will be month, and this will be month, and this will be day, and this will be day. And then when we're done, we can just drop the original date column, because we've now generated these new features from it. So actually df.drop date from axis 1, and delete that. And now we'll take a look over here. Date is gone, and now we have year, month, and day, and they're already in integer form. So just like that, we have processed that section. Now what's left is encoding these categorical variables. So when we're thinking about how to encode, it's a very good idea to get an understanding of what kind of data lies in each column, more specifically. So we can create a dictionary that's going to map a column name to the missing values in the column. So if we get a certain column and type .unique, we can get all the unique values in a given column. So here we're mapping a column to the unique values in that column, but let's actually get the length of it first, just to see like how many unique values are in each column. That's for every column in x.columns. And here we go. You can see each column name along with how many unique values are in it. And this gives us a sense of how to encode these columns. You'll notice that there are no binary features. Binary feature is a feature with only 2 unique values. Those are particularly easy to encode because you just choose one value to be 1 and the other to be 0. But you'll see that there are no such features here. Instead, we have a lot of nominal features, which are features with more than 2 unique values, and their values do not take any particular order. We can get a little more information about the features here. For example, we have the suburb, which has 370 unique values, and they do not take any order, right? There's no ordering between the suburbs. The address, which has 44,000 unique values, and this is also nominal, but it's a little there's too many unique values in here to use our traditional one-hot encoding approach. Let's move on though to the others. Rooms, also number of rooms. So this is actually, you could consider this a categorical variable, but we could also just consider it numerical, since this is a continuous range. Well, it's a discrete range, but it can take on any numerical value, and there is inherent meaning between by having like a fewer number of rooms and a higher number of rooms. The model will be able to understand that duality there. For type, this one, it looks like there's 3 unique types, and here the type comes in, well, it says there's a bunch here, and maybe that's for the other data set, but there's definitely no ordering between these types, so also nominal. See method, this one has all the different methods, and you'll see that there is no order between these either, so that's also nominal. Seller, the seller G is the real estate agent, and that has 422 unique values, but no ordering, so also nominal. Postcode, this is a zip code or some sort, and it is also nominal, even though it's in a numerical form, because this is not meant to be understood as a continuous range, right? We don't want the model to think that 3064 means less than 3199, right? These are sort of independent of each other. We want them in separate columns, so we're going to use one-hot encoding. Then we have region name, property count, distance. Region name, this is also no ordering, just different values. Property count, this is a numerical value, so we're not going to mess with it. This actually is a count, so we're going to leave it as it is. And then bedroom, I don't think that one's in our data set, but distance, council area, let's see. Distance, this is also in kilometers, so that's a numerical value. We're going to leave it as it is. And then council area, this is also going to be nominal, because there's no ordering between these. So we have no ordinal features. Right? Ordinal features are features with more than 2 unique values, but also but they have some sort of ordering between their values. There are no such features here. These are all nominal, and that would apply to suburb, address, type, method, seller G, postcode, region name, and council area. So that was a bit of a mouthful, but let's go and grab all this. And what I'm going to do is we're going to one-hot encode nominal features. So what I'll do is I'm going to create a column dict. This is going to be a dictionary. I'm actually going to start it off with this. But this dictionary is going to basically tell us which columns we want to encode, and then what prefixes do we want to use. So I'll explain to you what I mean by prefixes. So pandas has a function called pandas.getDummies, which takes in a column. For example, let's use the suburb column. Actually, method might be better. We'll do method. So df sub method, and we're passing it in to getDummies. If we look at the original method, actually this shouldn't be df, it should be x, right? If we look at the original method column, you see it has some of these unique values. We can actually get all the unique values with .unique, and there are 5 different values. Now if we get the dummies for the column, it takes each unique value and constructs a new column out of it. And then for each example, we have either a 1 or a 0 in a given column. In fact, actually, there can be only 1, and all the rest is zeros. So if we look at the data, right, here's the type, method. We have S, 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 and then at the bottom we have PI, SP. So over here we have 1, 1, 1, 1 in the S column, and at the bottom we have, well, I think we may have dropped that PI. But for SP, we have a 1 here because that corresponds to an original value of SP in the method column. So this dummies is a way of giving each unique value its sort of its own column, its own feature, so that they are not confused for being part of a continuous range. And this works very well, especially when you have a small number of unique values in a given column. For most of these, it will work. a few hundred is fine, but for this one, address is causing some problems. 44,739 new columns added to our data will take, it's going to be a lot more features than we want. It will slow down the performance of our model, and it may actually negatively affect the performance because it will confuse the model with too many features. So what we can do here is use a different encoding scheme. I don't want to lose the address data. I was experimenting with it earlier, and keeping the address actually does improve performance, but I'm not going to use one-hot encoding for this one. So let's go ahead and remove address from here. Too many values. Then we'll go ahead and also remove all the numerical variables, the ones that are not categorical. So rooms was numerical. Which one else? Property count was numerical, distance was numerical, and then these year, month, and day we already encoded, so we're not going to use those. So I believe these are the remaining ones, and these are the 7 nominal features that we will be one-hot encoding. So now I don't want to map it to its unique values. Instead, I want to map to a prefix. So let me show you here. This was our dummies. If we include a prefix in the function, let's say me for method, all that will do is it'll append this little prefix me to the beginning of each column. So this is useful if you're encoding a bunch of different columns. We know where the one-hot columns come from, which column each one-hot column comes from originally. So what I'm going to do is I'm going to map a column name to the prefix we'll give it. So we'll just use the first 2 letters of each one. This will be SU. We'll make this TY. We'll make this ME. This will be SE. This will be PO. This will be RE. This will be CO. Okay, and now I'm going to create a function up here called one-hot encode. It's going to take in a data frame and a column dict. So we're going to pass in this column dict into our function here, and it's going to one-hot encode each column with the given prefix. So we'll start by creating a copy of the data frame we pass in, and then for every column prefix pair, in column dict dot items. So this dot items will return the values of the dictionary as tuples, key value pairs, but as tuples, so that we can iterate through 2 at a time like that. And then we can continue by creating dummies for each one. So for each pair of column and prefix, we'll create the dummies with pandas.getDummies for df subcolumn and the prefix given by prefix. Alright, then what we'll do is we'll take the data frame and we'll concatenate with pandas.concat the original data frame and the new dummies columns on axis 1, so side by side. So this will just basically paste on the dummies to the right side of the data frame, essentially adding the new one-hot columns. And then when we're done, all we have to do is drop the original column from which we created the dummies, because it is no longer useful. And then we'll return df. So that's going to apply all of our one-hot encoding in one go. We don't have to do it column by column. All we do is specify a column dict, and it will take care of the rest for us. So we'll run that, and then down here, df equals one-hot encode, that's our function, passing in df and column dict. Alright, so now if I run this, and then down here, check out what x looks like, we now have 1,000 different columns, and they're almost all numerical. At the end, the only one that's not numerical now is the address column. Everything else is numerical, and a large majority of these are one-hot columns. We have the year, month, and day at the end, and a few of the original numerical features at the beginning. But everything in the middle is one-hot columns. And the last thing to deal with now is the address. So the address is a little trickier, right? We can't just one-hot encode it because there's too many values. So what we're going to do is use a dense encoding for the address column. Now what I mean by that is each a one-hot encoding is also called a sparse encoding. And the reason it's sparse is because there's so many zeros in here. It's very rare that you see a 1. If you look at the whole bunch of one-hot vectors here, right, you can for a given variable, you could consider one of these a vector. Can I use up here again, right? So this is for a single variable, right? This is just the method. Oh, hold on. Let's do it on data. Okay, here's just the method data, one-hot encoded, right? So each example has a vector, essentially, associated with it. And this is a sparse vector. Sparse because there's only one 1 and all the rest are zeros. Now, this is okay, especially when we have a small number of unique values, because the vector only takes 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces to represent it, right? However, when you have a huge number of unique values, each vector for a single address would be of length 44,739, which is just, it's too much, right? So what we're going to do is instead encode it in a dense format, which means just many fewer spaces to encode, but you can think of it as each address is represented by a vector in a smaller dimensional vector space. So let's say we pick a 3-dimensional vector space. That means you take a 3-dimensional space and you send each address to a different point in 3-dimensional space. And that only takes 3 numbers for each address to be represented. So the way we're going to accomplish this is by using a keras embedding layer. So tf.keras.layers.embedding. So you'll see this is a layer from keras that takes in an input dimension and an output dimension. The input dimension is essentially what was the dimension of the original sparse encoded space. So for method, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, because it originally took 9 spaces to represent it. And the output dimension is of our choosing. We can choose to represent it in any dimensional space we want, and generally the higher dimension you pick, the more information can be carried by these vectors. So we'll come back to this later. The added bonus about this layer is that because it's in the model, it will actually learn where to send the words. In this case, the address. It'll learn where to send the addresses in the dimension space of our choosing. So we don't have to worry about actually like telling the model where to put them. We just have to give the ability to do that, and it will tweak the weights accordingly. So all we have to do then is set up this address column in such a way that the model is ready to receive it. And what we want to do for that is we want to encode each one of these individual words inside the address column. So 49, Lithgow Street, 59A, Turner Street. Each one of these individual words we're going to represent with a different unique integer. So I'm going to create a function here called, I should do it down here, get sequences. And I'm going to pass in a column or a list of texts, and we're going to return the sequences. So what this is going to do is it's going to take a given address and it's going to map each unique word to a different unique integer. And then we're going to return the sequence of integers in the end, because we can pass integers into the embedding layer, whereas in its current state we can't just pass in string data like this. So for that, we're going to use a tokenizer from keras. And the tokenizer is basically just going to do what I explained. It's going to take each, here, why don't I just keep this up here. We look at just the address column. It's going to take each unique word, any one of these words, in fact every one of these words, and it's going to map them to a new spot actually just to a new unique integer. So the way we do that is we're going to fit the tokenizer.fit on texts, passing in texts. So we're going to fit it on the text we pass in, and then we're going to create some sequences using texts to sequences. So after we fit it, we can then transform the texts and store them in sequences. And if we just look at what that does, let's say we pass the address column in to this function, get sequences, passing in x address. It should return a bunch of sequences for each address, like I said. So 49 went to 66, Lithgow went to 2804, and street went to 1. And this is actually done in order of frequency. So the most common word will be assigned to 1, the second most common word will be assigned to 2, third most common word will be assigned to 3, and so on. And so you can see that 1 corresponds to street because that shows up the most. I believe 2 corresponds to road because that's the second most, and so on. And we can actually get an index that describes the ranking of each word from tokenizer.wordIndex. And I'm not actually going to look at it, but that's essentially just a mapping from each value to its corresponding word. Now if we get the length of this, we'll actually get the total number of unique words in the whole column, right? And so I want to sort of print out the length of the vocabulary, vocab length, given by the length of tokenizer.wordIndex. Why don't we actually just store that in its own variable, call it vocab length. However, so let me just vocab length. Yeah, let's just run this. Then it should print out before it shows us the sequences. There are 10,000. Put a colon there. 10,773 unique words in the list of addresses. So this is going to be our input dimension. To represent a single one of these, any one, it will require 10,773 spaces in a sparse encoding. Right? So if we had a vector like this to represent each one of these, each one would need 10,000 different values, all being zeros, and only one of them is a 1, if we're doing sparse. So that's our input dimension. And then what we're going to do is, you'll notice these are all of varying length. I mean, many of them are 3, this one's 4. We want to find the longest one, and then we're going to pad each one so that they all take the same length. So what we can do to get that, we'll call it max sequence length. Will just be if we take we can use a list comprehension to get the length of a given sequence for every sequence in sequences. And then we get the max of that, numpy.max. That will give us the maximum sequence length. Right? It'll be the max of this list, where the list is consisting of all the lengths of every sequence. And then we can use the pad sequences function from Keras that I imported earlier to pad the sequences with a maximum length given by max sequence length. And padding equals post will ensure that the zeros go at the end of the sequence. And so that's going to be our new sequences variable. Alright, and let's just print out the max sequence length as well. Max sequence length. Okay, now if we get the sequences, we have the same input dimension, maximum length of 5, and now each sequence takes 5 characters, and they're padded by zeros at the end where there originally weren't. And now I just want to note, because we added this new 0 character to our vocab, we have to actually do +1 on the vocab length. to give for that extra 0 character that we now have from the padding. So now if we check this, this is our total vocab length, our maximum sequence length, and the actual sequences themselves right here. So that was a lot, but now we are ready to actually get them. So let's get address sequences. So we're going to use this function we made here, get sequences. We'll call it addr sequences equals get sequences for df sub address. And when we're done, we can drop the address column because now we have the sequences for them. So we're dropping from axis 1. And then, let's see, I want to return it separately. So we're going to return address sequences after x, like this. So now we're going to return 3 values. We have the x, we have the sequences, and we have the y. So this model is going to take in 2 different inputs. The x, which is all the regular data, and then the address sequences, which is this little added the column that has been encoded in sequence form. Alright, so we'll run that. We'll run this if it hasn't been run already. And I guess let's run this. We've had to make sure that we're also getting address sequences. And take a look. Okay, fantastic. So the sequence column, the address column is gone. This is fully numeric data now, so it's ready to be fed into the model, or just about. And then we don't need that, sorry. But now we also should have addr sequences, which is the sequence data for our addresses. Alright, so the last thing to do is scale this data. So just the x. Scale x with a standard scaler. So a standard scaler will ensure that every column has a mean of 0 and a variance of 1. And the models tend to perform much better when each column takes on a similar range of values. So right now it's all spread out. These columns only take 0 or 1, whereas this one goes all the way up to 17,000. So the standard scaler will ensure that all the columns take the same range of values. We'll create a scaler, the standard scaler object. This is from sklearn. I imported it earlier. And all we have to do is call scalar.fit transform and pass in x. And that will apply the transformation to x so that each column has mean 0 and unit variance. And then that's going to be our new x. Now this actually returns a NumPy array, so I'm going to turn it back into a data frame and keep the column names the same as they were before. So now we run this, and you'll notice here's the old x. Now we check the new x. Just let that finish. Check the new x. Each column now takes a very similar range of values, so that we have mean 0 in every one. And you'll notice over here we actually have a value of 18, which means these are probably outliers. Is that possible? This is a 1-hot column. This is very strange. This has 22 as well in 1-hot columns. This is very interesting. Let me check the mean of each column in x. They're all incredibly small, incredibly close to 0. But this only takes 2 possible values, so how can it be a mean near 0? This seems fishy. Really? Let me try this one more time. Transform x. Yeah, it's there. That's very interesting. If I just grab that column, I want to see what kind of values it takes. Dot unique. Just 2 possible values. Dot mean. Oh, it's very interesting. Huh. There must be a tremendous number more zeros than there are ones. That's why we're getting such a high value for the ones. To ensure that the mean is pushed back over to 0. That's very interesting. Huh. I've never actually seen such high values in a scaled column before. Okay, but that will do it. Okay, so we have our X, we have our address sequences, we have our Y, and X is scaled, which means we are ready to begin the training. That was a long time pre-processing, but now we can start training properly. Alright, so last thing, I mean it's still sort of a pre-processing step, but it's related to training. We're going to make a split between the train and test set of our data. So I'm going to use the train test split function from sklearn. That's going to take in the data we want to split. It just has to be that each value we pass in has the same number of rows. So X, the sequences, address sequences, and Y. And we're going to split them so that there's a train set in each one with a 70% split. So 70% of each one is going to go to the train set, and the other 30% will go to the test set. And this function also shuffles the data for us, so we don't have to do that ourselves. And we can include a random state at the end here that will ensure that the shuffle and split always happens the same way, so that we can reproduce it. And then here I'm just going to split it, so xtrain, xtest, and then address train, address test, and ytrain, ytest equals train test split. So it's taking these 3 sets of the data and generating these 6 sets of the data, where we have a train set with all 3 and a test set with all 3. So there we go. We now have 6 sets of the data, and we can begin constructing our model. Now, so this is going to be our input. This is also going to be our input, and this is going to be the what we compare the output to, so the actual values that we're training with. So we need 2 different inputs, X inputs and address inputs. X inputs is going to be a tf.keras.input, and we specify the shape as xtrain.shape sub1. This is a vector of length number of features in X. So xtrain.shape is 33,903 examples by 1,069 features. So we're passing in, for each example, we're passing in a vector of length 1,069. And we can get if we do sub 1, we'll just get that value. So that's what we're passing in right here. And then similarly, instead of xtrain, we can do address train, which is 33,903 examples, each with length 5, 1 for each. Right, so there's 5 elements in each sequence. So this is going to be exactly the same, except instead of xtrain.shape, it's address_train.shape. So we have our 2 inputs. One's taking in values from X, one's taking in values from the address sequences, and then we're going to work with each one separately. So X first. For the X values, we're just going to have 2 dense layers. xdense1 and xdense2, and each one is going to be tf.keras.layers.dense, and we'll have 512 neurons for each one. This is a value that I found works, and we'll have a ReLU activation function on each one. Then to the first one we're passing in the inputs, and to the second one we're passing in the output from the first dense layer. And that's it for X. Now the address sequences. So this is where we're going to use the embedding layer that I was talking about. The embedding layer is going to be tf.keras.layers.embedding, and like I said, this takes in an input dimension, which is the dimension of our original sparse encoding for a given value, for a given sequence, and that would be the vocab length, or the total number of words there originally were, with the +1 added for the 0 character. So that's going to be our input dimension, and our output dimension is going to be our choosing, and 64 works fine. And we'll also pass in the input length. This is the length of a given sequence, and that will just be given by address train.shape sub1. Let's also name these. Just name them so that we can see it nicely later. This will be x input. Name is address input. This one can be x dense 1. This one's x dense 2. And then here we'll have the name address embedding. Okay, now we're going to, so I should explain the output of the embedding layer. We're passing in basically sparse representations of each word, and we're getting back a dense representation of each word. So originally it would take 10,774 spaces to encode a single word. Now it's only taking 64. So essentially we're getting these sequences where each word in the sequence is represented by 64 characters. So we have 5 words in each sequence, and each word has 64 different characters representing it, numbers representing it. So this will output a 64 by 5 matrix, and because that's two-dimensional, we want to flatten it into one dimension afterwards. So we're going to have a flatten layer that comes after it. This will just be tf.keras.layers.flatten, and we're going to pass in address embedding. We actually have to pass in the address inputs to this one. Alright, let's give this a name as well. This will be address flatten. Okay, and that's it. So this outputs a single vector, this outputs a single vector, and now we can concatenate the two vectors. Concatenate using a concatenate layer, tf.keras.layers.concatenate, and we pass in the vectors we want to concatenate. We'll pass in x dense 2, which is the output from our x, and address flatten, which is the output from our address sequences. And we'll give this a name as well, concatenate. And yeah, so now we'll create our outputs. This will just be another dense layer, but with only one activation, where the one here, the one neuron that it's outputting is actually just the predicted price, a given predicted price that we're going to compare to our y. And the activation here is going to be linear, which means no activation. It just passes right through, passing in concat, and then that value will be compared to y. Alright, now we'll create the model. tf.keras.model. The inputs are given by x inputs and address inputs. And the outputs are just given by outputs, which is the single output at the end. Alright, and let's print out a summary of the model, which will give us information about the parameters that will be tuned. And we'll also plot the model with tf.keras.utils.plotModel, pass in model. So here's the information. You can see we have weights that need to be tuned in the first dense layer, in the second dense layer, and in the embedding layer, and then again at the end when we create our final prediction. So here it is. This is what it looks like. We have our x inputs, which gets fed through two dense layers and gets concatenated, and our address inputs, which gets embedded and then flattened and then concatenated with the x, and then that final vector gets sent to a dense layer, and that produces our final result. So now we can compile the model. So we're going to use an atom optimizer, and I want to adjust the learning rate on this. tf.keras.optimizers.atom, and I'm going to pass in learning rate equals, we're using 0.1, this seemed to work the best, and then the loss here is going to be MSE, mean squared error, because it's just we're just comparing linear values, just this compared to our prediction, and we want to calculate the departure from those two values, so we'll use MSE. And then history is where we're going to store the model's fit history. Model.fit. Here we're going to pass in the inputs, which will be the train set for X and address. That's our inputs. And our outputs will just be Y train. And we'll include a validation split of 20%, batch size of 32, and we'll train for 50 epochs, but include a callback function, tf.keras.callbacks.early stopping, which will look at we'll monitor the validation loss, and if the validation loss does not improve for 3 epochs, we will stop the training and restore the best weights. So the weights from the best epoch will be restored after 3 epochs pass with no improvement to the validation loss. And we're also going to include a callback, reduce learning rate on plateau, which also looks at the validation loss by default, and it will lower the learning rate when it notices that we're not seeing improvements, just to allow us to converge more nicely before we're forced to early stop. Alright, so let's train. Let's see what we get. Alright, so we have a very high loss, you'll notice, but this does not necessarily indicate that we have a bad model. We'll get the results down here while that trains. I'm going to create the true values for our y, which will just be given by yTest, and I'm going to turn it into a NumPy array. And then our predicted values will be given by model.predict on the test set. Now we got to pass in xtest and address test to create predictions from. And this will return, it actually returns a 2-dimensional array. I'm just going to squeeze it with numpy.squeeze so that we remove that extra dimension, and it will just return a 1-dimensional array. The reason for that is when we compare the two using the R2score function, which I imported earlier from sklearn, it requires that both are of the same dimension. So we'll pass in yTrue and ypred here, and we'll store that in model R2, and we'll print out the result, which is model R² score. You'll notice the model stopped training because the validation loss, it reached a minimum here and then did not improve for 3 consecutive epochs. So it's going to stop the training and restore the weights from this epoch, which was the best. Model R² score, here I'll format it to have 6 decimal places, and we'll format passing in model R2. Oh yeah, I have to create the predictions first, and now check it. And we get an R² score of 0.73, which is actually quite good considering how high our loss was. So yeah, after all that work, we have a pretty decently fitting model, and there actually was an increase of about 0.02 or something in the R² score when we added on the address features. So I tried it first with just the X, and we actually did get a lower R² score. So it seemed to be worth it to include this this extra input to improve performance. So that will conclude today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.